No telling how long this is going to live in perpetuity or be used to tutor kids, but here we go. All right, we're talking about chemical reactions. Get ready to take some notes. People, you need to be off the blank BOCW page and into your regular chemistry notebook where you can take notes. And here's a note for us to talk about reaction spontaneity. All right? Something that's spontaneous occurs with no outside intervention. Now, I know you've heard about the term spontaneous. I know you've heard about that term being used to describe a person. Well, it's also can be used to describe events like chemical reactions. So, a spontaneous chemical reaction happens on its own. No one needs to make it happen. For example, if you leave iron out in the air and in the elements, it will spontaneously occur. And most spontaneous reactions are exothermic, but not all of them. And the funny thing is, because I've looked this up, you can Google most spontaneous reactions are endothermic, and it'll give you some information. And then you can turn around and Google most spontaneous reactions are exothermic, and it'll give you information. But this is what I believe to be true. So, iron rusts. You don't need to help it rust. There are some things you could do to help something rust if you really, really wanted to. You could put some salt in there, right? So, when we talk about spontaneous reactions that happen on their own, can you think of something else? What if you opened a soda and left it sitting? Tell me something that would happen. It would go flat. Now that's a process. That's not a chemical reaction. That's just the gas coming out of solution, right? Yes, sir.
Maybe like group 1 element reacting with air.
Yeah, if you had a group 1 element and it got wet, it would spontaneously generate hydrogen gas and react with the water. Absolutely. So those are what we mean by spontaneous reactions and reaction spontaneity. Now we know about collision theory. We've mentioned it many times. When we are making chemical reactions occur and we want them to occur with a high yield, a high percent yield, and a high efficiency, we're looking for maximum collisions between of all the atoms and all the molecules in that area, correct? And we talked about this a bunch of times when we were making solutions and how can you make a solution quicker and better. So we can talk about what are some things that can affect the rate of a chemical reaction occurring. What are some things that can affect the rate of a chemical reaction? Temperature, absolutely. I like that. That's an excellent answer. Temperature can definitely control the rate of a chemical reaction. All right? Say you're somebody got something else. Say I'm trying to pressure. Yeah, there are definitely situations where pressure could affect the rate of a chemical reaction.
Surface area?
That's not really what I'm looking for, but I like it. Surface area, absolutely. Have you guys ever heard of plants, coal-fired power plants sometimes having explosions and people getting killed? Well, it's not that the boiler blew up. It's that there was just a spark in an open room. And in this open room, there was a bunch of coal dust. Coal dust is very flammable, and you can't see it in the air sometimes. It's so fine and so thin. So probably in the early 2000s, or 2008 maybe, we had a power plant out here, a coal-fired power plant in southeastern North Carolina, and there was just a spark that occurred in an open room, and the whole plant blew up because the surface area and the next word, coal dust has a lot of surface area, but there must have been a lot of it there for there to be an explosion, right? So what's the word for having a lot of something there and available? The concentration was high. So temperature, concentration, surface area, right? And look at number one. Number one is like so obvious that we kind of, and you can put it in any order, I don't care about your notes. But number one is like so obvious we didn't even think about it. But how explosive are the things you're using? Right? Like if you have a cup of water and a cup of salt, you're not making a big explosion. Because those two things don't have a chemical nature to react with each other. So if you want to have control of the rate of your reaction and the size of your reaction, how the chemical nature or the reactivity of the chemicals you're using is a big part of it. And then down here, a last one called a catalyst. And you know that we've catalyzed reactions in here already. And we're going to catalyze a similar reaction today. But this time we're also, and this is not going to amaze you, but we're going to quantify it. We're going to use a thermometer, okay, and get some numbers. And you'll probably be surprised, but we're also going to be able to graph it. So a large part of this, when we're talking about chemical reactions and their spontaneity and them being endothermic or exothermic, a lot of the stuff that we're talking about, we're going to be able to actually graph. You already know what a catalyst is. You don't need to write that down. If you have already put that in your notes, because we've talked about catalysts twice already in this course. But a catalyst controls the rate of reaction, but it's not part of the reaction. All right? A catalyst is the one kid in the background in the lunchroom yelling, "Fight, fight," trying to get the two kids to hit each other. They're not part of the fight, but they're making it happen. Does that make sense? All right. Boom. This is it. This little simple graph right here is the basic idea of the whole lesson. Okay? There's a line graph here, and there's a lot of information. So maybe don't write down anything for just a second and just watch. And then I'll give you a second to copy it at the end, okay? So just look up here. On the x-axis, right, we just have time going by, or the progress of the reaction. So you can just think about this as time going by. And on here, this is the energy. Okay? This is the energy. So a given that may not have occurred to you is that before the reaction happens, this is the amount of energy contained in the reactants in the chemical equation. Let's say we're mixing propane and oxygen. Well, molecules of propane and molecules of oxygen already have a certain amount of energy in them. Okay? And this amount of energy is due to their chemical nature and the quantity, how much we have, right? If you want a big explosion, you want a lot of propane and a lot of oxygen, right? So you have a lot of energy available. So before there's a reaction, we have to understand that this chart is not going to start at zero. If it's starting at zero with zero energy, there's only two options. One, you don't have any material there, or two, you're at absolute zero. Does that make sense? Okay. So we start here with some chemical reactants that have a certain amount of energy. And then okay. So here we go again. We're right here. This is the amount of energy that are in the chemicals that we're mixing. Now to get them to mix with each other, some energy has to come into the equation. Where does this energy usually come from? Even in a spontaneous reaction, where does this energy come from? From heat, from temperature, from things available, energy available around it in its environment. Does that make sense? Okay? So, some other heat, when these things get near each other and they want to react, they can draw energy from their environment. All right? This energy is called the activation energy, the amount of energy that's needed to put into these chemicals to get them to react. And then once you have enough activation energy, the reaction occurs. Okay? Now, if you look at this reaction, you can already tell just by looking at the graph that it is exothermic. How can you look at this graph and know that it must be an exothermic reaction? It loses energy. Look, we started out with this much energy, and then after the reaction, there's only that much energy in there. So this much heat came out. Does that make sense? This much energy is now missing. Where did it go? Into your finger if you were touching the test tube, right? All right. So this is, bye, have a good day. This is an exothermic chemical reaction that requires activation energy. And if we were talking about this, the red line here, we're talking about this red line, there's all sorts of questions we can answer. One, it's exothermic. Two, how much energy did the products have before the reaction started? Whatever number's here. Three, what activation energy was necessary? Well, that question could be asked to you in two different ways. It could mean how much total energy is needed for you to space out and look at your phone during the most important part of the reaction. Well, not much energy is needed to do that. But I could ask you a question that could be about this much energy, or how much extra energy is needed. That'd be this much energy. Does that make sense? Generally it means how much activation energy is needed to get these chemicals to go off is this number, the difference between what you have and then this much more is needed. Does that make sense? So that could be a number. This could be like 100 kilojoules. 100 kilojoules more was needed. How much energy was total given off after that point? That'd be from here all the way to here. Right? What is the net loss in energy? That'd be this difference right here, from here to here. Do you see all the different things?
Yeah.
Right? So now, there's another line on here that's a blue line. The blue line is the exact same chemical reaction with the exact same output, except for what's different about the blue line. It's catalyzed. The blue line is the catalyzed reaction. The catalyst, we know, is not part of the reaction at all. It just makes the reaction happen faster, right? We could also use a catalyst to slow down a reaction. But we generally think of a catalyst as being something that speeds it up, just because that's how we think. The catalyst is doing two things here. Can anyone tell me the two differences between the blue line and the red line? Because there's two.
There's not much more, like, extra energy, like, no activation more.
What? David, give me one.
The activation energy goes down.
Yeah, you only need this much energy now to make it go off, to make it react and give off heat, instead of that much. That's the first thing. So adding a catalyst lowers the activation energy. What's the other thing that it's doing?
It takes less time.
Yeah, it's also happening quicker. So it's happening easier and quicker. Does that make sense? So the time frame is shifted to the left and the volume of energy is shifted down. So catalyzing a reaction makes it easier to occur and happen more quickly. But what's important right here? What's important right here? They end at the exact same place, and they, yeah, so the catalyzed reaction basically is no different. It just happens easier and more quickly. Does that make sense? All right. take a look on this, and we're going to ask some questions. I'm going to ask you some questions on the next slide, all right? All right? Let's take a look at this, and we're going to quantify this. I'm just going to ask you questions out loud because I'm recording this lesson for kids at home. All right. Question number 1. Think about it for a second, and then raise your hand if you know the answer. How much activation energy is needed to start this chemical reaction? How many more kilojoules of energy are needed? Parker? 20. We're starting at 25. We already have 25 kilojoules of energy, but it's got to get up to 45 before it can react. So 20 joules of activation energy are needed. Is this a catalyzed or uncatalyzed reaction? We don't know because there's nothing to compare it to, right? Okay. Is this reaction endothermic or exothermic? It's exothermic, correct? Because here's where we start and here's where we end. What is the total net loss of energy in this exothermic reaction? 20, because it starts at 25 and it ends at 5. Does that make sense? And then look at this little blip, which you probably won't see as a question from me, but is a very good question. If we wanted to reverse this reaction and make it go backwards, because we're getting ready to deal with reversible reactions, it would take 40 kilojoules. Because we're at 5, we'd have to get it back up to 45 to get it to go backwards, if this is a reversible reaction. Does that make sense? All right. And then here's the question to Green. It says, what is the value of delta H in the reverse reaction? Plus 20 kilojoules. In the forward direction, minus 20 kilojoules. Does that make sense to everyone? All right, that's activation energy and kind of how it works.